Welcome back. I'm Steve Brunton from the University of Washington, and this is the second half of a new course on probability and statistics. This is one of my absolute favorite topics in all of mathematics. It is incredibly useful. It's up there with calculus, linear algebra, and differential equations as one of the pillars of how we model the real world, especially how we model systems that are too complex to handle with our kind of classical deterministic methods, okay? And so this is kind of the overview of the second half of the course on statistics. So we spend a lot of time, by the time this video comes out, you've probably seen that there's a whole series on probability. I'm guessing about 10 hours of lectures on probability theory. And now we're about to launch into kind of the dual problem of statistics. This is where the rubber hits the road. So probability is all about mathematical modeling, combinatorics, distributions. It's really elegant theory. So I'm actually going to write this down. This is all about modeling uncertainty in the real world, building models. And statistics is all about data, okay? So this is really important for us in the modern machine learning era as data scientists. Statistics is all about taking data and saying something about the probability model. So probability, you assume you have the model, you assume you have the distribution that's known, and we don't know what the samples or the data are going to look like, but we want to say what is likely. That's a probability problem. The dual of that, the flip side of that, is the statistics problem, where now we have data, we assume that samples and data are known, and we want to infer something about the underlying probability model, the parameters of the system, something about the system from data. So these, of course, are kind of dual problems. They're intimately related. And so you need to know these foundational probability concepts to do good statistics. But statistics is really where we start being able to make powerful predictions, decisions, estimations. And again, it is the basis of modern machine learning is statistical data analysis. Okay, so this is one of my passions. I love this. I learned this over 20 years ago when I was at the University of North Texas from Dr. John Quintanilla. So I want to give mad shout out to Dr. Q. Again, I'm going to base a lot of what I'm doing on what I learned from Dr. Q's notes in the University of North Texas. In fact, I was going back through this the other day, brushing up on some topic like random walks or Markov chains. And I actually found one of, I think, the first times I wrote down Eigensteve. So I think that this might have been, I was sitting in this class back, when I was 17 years old. I think that might be where Eigensteve actually comes from. So anyway, I want to give a ton of credit to Dr. John Quintanilla, who taught me essentially everything I know about probability and statistics. So anything interesting and correct I'm saying is probably him. Anything incorrect and misleading is probably because this is 20 years later. But I'm going to specifically take this modern perspective that what we really want to do is start driving towards big data and really complicated or nasty probability models that don't belong to the classes of easy classical probability models that we have been analyzing, things like normal distributions, exponential, Poisson, et cetera, et cetera. Those are still super useful for tons of real world problems, but there are other real world problems where the probability densities don't have a nice analytic closed form expression, and you have to learn them from data using machine learning. So this is all going to build towards that, but we're going to start with foundational statistics. Okay, good. So I think I just want to tell you kind of the outline of this class. Again, this was about 10 hours broken into 2 modules of intermediate and advanced. Statistics is going to be about the same. There's going to be kind of a core 5 hours that you need to know. That's kind of the intro, intermediate. And then there's going to be advanced topics that are, special topics and more technical. So you can kind of pick and choose your own adventure of how much you want to learn. Okay. But I really want to make this as targeted as possible. So if you have 5 hours, I want you to get the best 5 hours of probability or the best 5 hours of statistics that gets you as close to being able to use this as possible. And if you have another 5 hours, go deeper. And after this, there will be a bunch of special topics, things like stochastic differential equations, Markov chains, Monte Carlo, optimization for Bayesian methods, machine learning. There's an unlimited amount of cool stuff. So I'm just going to keep adding for a long time, hopefully. Okay, let's get into it. So given data, given data of a system, some things we can do. Some things we can do. This reminds me of a Deltron song, things we can do. And I'm just going to start going in order. Okay, so the first thing we can do, and we're going to start here actually because this is where the statistics is the easiest. Just like in probability, we started from the intro kind of baby steps, and then we worked up very quickly to some pretty advanced concepts. We're going to do the same thing here. So we're going to do something called survey sampling. So we draw a small sample from a large population. So if we draw, so this is essentially another way of saying, survey sampling. So this is called survey sampling or polling. And the idea here is, what can we say about the larger population from the small sample that we draw? And how big is a big enough sample to say things with statistical confidence about this larger population? So some of the things we're going to do, for example, there is this notion of a sample mean. If I have this sample, I can take the average. Maybe I'm measuring, people's political preferences or the height of an American, which clearly follows a normal distribution, and I might draw a small sample of 100 people to try to say things about the larger population distribution. So there's this notion of something called a sample mean. It's a really cool idea. You literally take your small sample, the variable you're measuring, and you take the average value. It's just the mean of your sample. Sometimes we call this X bar. And in the last set of lectures in probability, this kind of culminated in something called the central limit theorem, which showed that this sample mean from actual data tends to be distributed as a normal random variable, where the mean of this normal distribution is the mean mu of the population, of the true population, and the variance of this random variable is sigma squared over n, where n is the sample size. So this is the kind of thing you can do with statistics. This is kind of where we're going to start off. We're going to take a small sample, compute its mean, and we're going to show with the central limit theorem that that's a normally distributed random variable where mu and sigma squared are the population mean and variance, and n is the sample size of the sample I took to compute this mean. This is incredibly powerful, and this allows me, because I have this variance here, it essentially says that this variable will converge to the true mean. If I take the average of a sample, it will tell me something about the average of my population. And the variance tells me how close to the true value I am. How big of an n do I need for this variance to be small? How much wiggle room do I have in this estimate of the true mean for a given n? So this tells me a lot of useful things. It tells me how I might design an experiment if I want a certain amount of accuracy or uncertainty in my estimate. Really, really important. And this is a simple place to start, is survey sampling. Okay, good. And this is true for any distribution of my data. It doesn't have to be from normally distributed heights. I can take samples of a large population that has some weird distribution, and that sample mean will still be a normally distributed random variable by the central limit theorem. That's the power of probability, are things like the central limit theorem, which are extremely general, powerful statements about arbitrary data and distributions. So that's our starting point. 2 is going to get even more interesting. Okay, so this is just kind of laying the foundation with some easy math that ties back to probability, ties data to probability. Now, we're going to start doing hypothesis testing. So testing hypotheses, and this is literally called hypothesis testing. And the hypotheses, there are so many of these you can write down. I'm just going to give a few to give you a flavor of the kinds of things we're going to be able to do. Really, really powerful things. Does a drug work? Okay, so let's say that there's some new super drug that is supposed to cure cancer or, cause incredible weight loss. Does a drug work or not? This is something we can test with statistics. We can essentially have a control group and a treatment group and test if their means are different. That would indicate that the drug did something. That's a hypothesis we can test using these distributions, using literally a normal distribution. Did a marketing campaign work or not? So did a marketing campaign increase web traffic? This is just an example. This is what we call A/B testing. So this is A/B testing in like computer science, where you have, you do a modification, you change something about your website, and you see if people click on, ads more. That would be A/B testing. A drug working or not, this is a control versus treatment group. Okay, this is kind of, you'd have a control group and a treatment group. Other things you can do, one of my absolute favorites, actually have been thinking about this a lot lately, is are two distributions the same? Are two distributions the same? And this is what is called the chi-squared test, is going to tell us that, the chi-square test. And the chi-square is a distribution from probability that allows us to test a hypothesis using data. So that becomes statistics. Really, really important ideas here about testing hypotheses with data based on probability models of how that data should behave. You can test lots of cool hypotheses. And this, again, generalizes to machine learning when those distributions are empirical distributions. You can really think of machine learning as having empirical distributions from data. Okay, so you get empirical probability models from a wealth of measurement data. So testing hypotheses is going to be a big, big deal here. And this also allows you to quantify how significant your results are. You don't just test these hypotheses, you get like a confidence of how likely the drug is to work or not. Like, am I 95% confident in this result? Am I 99% confident? You get a notion of statistical significance. So you can quantify how significant a result is. Okay, and this leads very naturally into something called experimental design. Super important if you are going to run a drug trial. Let's say that you think you have a new super drug, or let's say that you have a new super composite. It's going to make aircraft lighter and stronger. You've got a new material or a new drug, something new that's going to be amazing. And you need to convince the world that it's safe and it works. You need to design a statistical experiment, a data collection protocol, and a hypothesis to test so that you can convince people with some amount of significance of your result. And that is all about designing a statistical experiment to be honest, to be accurate, and to be significant so that you can convince other people of the effect of some, new drug or new material or new whatever it is. Okay, so experimental design is super important. And the dual of experimental design, the significance level that we quantify in a hypothesis test is usually called the p-value. You've probably heard of the p-value before. A p of 0.05 is a statistically significant result, meaning there's like a 95% chance that, I get the correct answer if I say something happened. And so what that means is that a lot of people do bad statistics called p-hacking, where they do bad experimental design. They do either through fraudulence or ignorance, they do a bad experimental design to get a p-value that's significant even though their experiment was wrong. Okay, so there's lots of ways of getting significant statistical results by doing bad statistics. I'm going to tell you about those pitfalls. We're going to code this up. All of this, we're going to have examples in Jupyter, in Python. We're going to actually, code up, because this is data and testing. We're going to build code to do all of this. And I'm going to show you in code what p-hacking looks like and what to look out for so that you can not fall into those traps of fraudulence and ignorance. Okay, super important stuff. And now the other kind of big part of this that I want to talk about, I think this is really, really cool. Maybe I'll go over here so I have a little more space, is this notion of fitting distributions and estimating parameters. So kind of the third big topic we're going to talk about is fitting distributions. And I'm putting it here under machine learning because this is really the intro to machine learning. Fitting distributions and estimating parameters, parameters. Good. And so probability essentially involves, this probability model, this probability density, probability of x, my random variable, given some parameters, theta. So I'll just label these really quickly. So this is my data given my parameters. These are the parameters of my probability distribution. So in the Gaussian example, this would be the mean and the standard deviation, things like that. Statistics is the flip of this. So statistics is all about finding the probability of my parameters given my data. So it flips this on its head. It's this notion that given data, I want to find the best fit parameters, the best distribution that fits that data. That's the statistics problem here. And this really is very much a Bayesian perspective. This is literally the Bayesian inverse of this. So we're going to use Bayesian ideas a lot in statistics because we're trying to kind of flip the paradigm where instead of estimating what the data should look like given a distribution with fixed parameters, we have data and we're trying to estimate the parameters from that data. Okay, so that's what we mean. And we're going to look at a bunch of examples here of how to do this. Things like the method of moments. You've probably seen this before. You might have. Method of moments. Very closely related to this sampling statistics here. You literally estimate things about your population from things like the first moment, the sample moment, things like that. We're going to talk about maximum likelihood estimation, max likelihood estimation, MLEs. This is a big, big, big topic. MLEs are a super powerful way of turning this problem into an optimization problem, which means we get all of the power of modern optimization, machine learning, and data to solve this problem. So maximum likelihood estimates is a big deal. And this also transitions very nicely into the Bayesian perspective. We're also going to talk about things like goodness of fit and hypothesis testing. How good is a fit? So once I've fit these parameters, how good is the fit, goodness of fit, and hypothesis testing. Confidence intervals. So once we get an estimate of these parameters, we can also give confidence intervals of kind of like what's the range of theta we think. So not just a fixed theta, but maybe I have a distribution of what I expect theta to be. That's kind of also the Bayesian perspective. I might have confidence intervals here. Confidence intervals on theta hat my estimate. Confidence intervals and hypothesis testing are really dual problems related to this p-value. And then we're also going to talk about something super important. I'm just going to actually put this in pink because it's so important, is this idea of bootstrapping and simulation. Bootstrapping and Monte Carlo simulation. Simulation is the key word here. So oftentimes there's things I want to know about my statistical distribution, like I might want to know, the variance of this parameter estimate theta, and I can't compute it using pencil and paper analytics. So I'll actually set up a big simulation, a Monte Carlo simulation, to get a bootstrap estimate of the distribution of my uncertain parameter. And again, this is the basis of a lot of modern Bayesian statistics and Bayesian machine learning, is doing these Monte Carlo simulations and bootstrapping. So this is kind of going to be an advanced topic that segues us into how to do computational statistics with big data and nasty distributions. Pretty cool stuff. Okay, then I guess we're going to keep going. I'm almost done. Topic 4 is going to be, all about Bayesian statistics. Bayesian statistics. And I'm going to have Bayesian statistics kind of woven out throughout these lectures. So we're going to get, an intro to Bayes in this statistics module. But realistically, we're going to have a lot deeper dives into Bayes later in my optimization bootcamp, in physics-informed machine learning. Bayesian frameworks allow you to take prior knowledge. Maybe I know something about the distribution, or I know something about theta, or I know something about the physical world. It allows me to build in that prior knowledge to these statistical estimates. That's a huge topic in optimization, machine learning, physics-informed machine learning. So this is also going to be something we cover a lot more later. A good way to think about this is probability tells me a model of how I think a fair coin or a biased coin will behave as a Bernoulli random variable. We have a model for this. And if I flip this coin 10 times, then the number of heads is going to be a binomially distributed random variable. And if I flip it 100 times, that binomial starts to look like a normal distribution by the central limit theorem, things like that. The statistics view is a little bit different. Let's say I have this coin and I flip it 10 times. Let's say it comes up 10 heads in a row. The statistics question is, do I think this coin is fair? What do I think the probability is of getting heads versus tails? Can I estimate those quantities and those uncertainties? Bayesian statistics is a really important way. If I flip a coin and it is heads 3 times in a row, some of these statistics methods kind of will fail and incorrectly assume that the parameter theta of how likely it is to flip a heads is equal to 1. It's always going to flip heads. And that's bad. Bayesian statistics allows me to bake in prior knowledge. If I just see a coin, if I feel a coin, my pretty strong prior is that it's a fair coin. So even if I flip 3 heads in a row, that's not going to shake my foundational belief in this coin being fair. It's going to take a lot more evidence for me to update my prior and say, oh, maybe if I get 15 heads in a row, shit, this is probably not a fair coin, okay? So Bayesian statistics allows me to build in a lot of prior knowledge to robustify and improve statistics when I have that prior knowledge. Now, this relies on you having good prior knowledge. Bad priors cause bad statistics. And then, there's going to be a lot more. This is going to be more and more and more. So we're going to talk about tons of interesting advanced topics that I find interesting, things like Benford's law. I love Benford's law. It's incredible. Markov chains are ways of kind of merging differential equations and probabilities. We'll talk about random walks. We'll talk about Gaussian processes for, again, stochastic differential equations, and much, much more. And eventually, what we're really getting towards is modern statistics and data analysis, which is, we call this machine learning, fitting empirical distributions from data. I'm super excited to walk you through this. This should be about 10 hours, kind of intermediate and advanced. This is going to give you a set of tools like calculus, like linear algebra, like differential equation to really model the real world and its complexity and its uncertainty from data. I'm excited to share this with you. I hope you're excited. Stay tuned for more. Thanks.